Let's now discuss a spiral mode approximation. And I'm going to follow what Warren Phillips does in his Mechanics of Flight book. This is his approximation. Now, there's a more traditional one that is used a bit more widely, but he contends that this approximation is a bit better. And, not having studied it much, I would just assume he's probably right. He's looked into this stuff pretty deeply. So anyway, I kind of trust him. So I'm just going to walk through the basics of it. Again, I'm not going to derive the entire thing, but I'll just walk you through the basic idea. So the spiral mode is really slow divergence or really slowly convergent. And so your rates are usually pretty small. So we're going to assume that delta beta hat, delta p bar hat, and delta r bar hat are 0. Okay, so and by the way, I'm going back to the linearized equations of motion here, not the eigenproblem. He actually starts from these linearized equations of motion. And remember, we're neglecting these terms over here because we're looking at the homogeneous form without any control input. So anyway, we set those three to 0 because the rates, we don't really have rapid changes in beta, p, or r. And so we're setting their derivatives with respect to time to 0 for this approximation. Okay, so when we put zeros in there, and then one other thing, we're going to say tangent of theta naught is 0 here. So we're looking at steady level flight. And just that alone actually decouples this, this fifth equation here. What we get out of that is that delta phi hat is equal to delta p bar. Okay, so hopefully you can see that. We've got a 1 here, so delta phi hat is equal to, we've got this 1 in that location there, delta p bar. Okay, so that's one thing that we need. And then it turns out that the top 3 equations here decouple from, are just algebraic equations. So these 3, that all is just 0 here on the left-hand side for those 3 equations. And then we can look at these 3 equations up here, multiplied by this vector here, and that whole thing has to be equal to 0. Well, it turns out that there's nothing in this column here, nothing in that column here, and so we don't have any dependence on psi or delta cy. So those two don't matter, and so what we're left with here is these 3 equations and 4 variables, and we can I could write those out. So it's going to be the cy beta times beta plus cy p bar times p bar plus this term times r bar plus this term, and by the way, theta naught is 0, and so cosine of that is 1. So it's times delta phi, and then each of these terms times these 3, each of these terms times these 3, and then we could back solve. So we could solve, for example, for delta beta, because these 3 equations all sum to 0, right? So each of those individually sum to 0. So we could use one of those equations. For example, we could use this equation here to solve for beta in terms of p and r. Then we could plug that into this equation here and solve for example, p or r in terms of the remaining variable. And then we could plug both of those solutions into this final one here to get to basically get rid of these variables. And so what he says is that you can work through this to get an equation that looks something like this. So we'd have delta phi hat is equal to minus r gy, that's one of those ratios, times we'll have cl beta times cn r bar minus cl r bar cn beta divided by cl beta times cn p bar minus CL P bar times Cn beta. Okay, so we're going to get a delta phi hat is equal to all of this times delta phi. Okay, and that's after we've gotten rid of all these other variables and back solve. So actually it simplifies down to a rather simple equation. And from this, actually, this is our eigenvalue. So just this term right here turns out to be the eigenvalue. So the dimensionless eigenvalue for spiral is simply what we have right there. So I won't repeat it. It's just everything there. The minus RGY times everything in parentheses. And then we can use that. Of course, that's a real value. All of these components are real inside of this, so we don't get any imaginary components. And so again, this is for a traditional aircraft because the roll mode is so heavily damped, and because the roll and spiral mode come out as a pair, an eigenvalue pair, the spiral mode must also just be a real value, so it doesn't have any imaginary part. And so so then our dimensional damping rate sigma is equal to, once you multiply, so we're going to take minus 2 v naught over bw. That's how we redimensionalize it, times lambda s, right? So we're going to plug that in there. And so this is just going to be equal to g over v naught times everything in parentheses. And I won't rewrite that, but it's all of this stuff here in parentheses. Will come down to these parentheses here. Okay, so that will give us, so it's really this stuff in these parentheses that you want to be looking at when you're trying to change your spiral mode. So if you want your spiral mode to be convergent, if it's right now divergent and you want it to be convergent, then you look in here in order to change that and try to change the sign here of course the sign tells us whether or not it's convergent or divergent, and so it depends on the relative magnitude of the parameters inside of here. So you can play around with that a bit in order to make it more convergent, or if it's too convergent and you want it to loosen up, you can make it more divergent. So anyway, so this is the closed form approximation for the spiral mode.